Okay, so it says the solar propulsion is switched on when the speed is 1.2 times 10 to the third meters per second, right? Okay. And then they say, what is the speed of the spaceship? This is for F, right? What is the speed when the xenon fuel has all been used, right? Okay. Well, now here's the thing, right? The area under a velocity graph is displacement, right? Area under an acceleration graph is delta V. So this is displacement, right? Area under an acceleration graph is delta V. Okay, so the way I did this was, of course, I was like, I must find the area under this graph. So I did what I always do when I find area under a graph, is I divided it into little rectangles like this. Okay. Notice that one of my rectangles is not the same width, so I have to account for that, right? And what I did was I read this thing. I read this. So this was 8.3, I thought, you know. Is that right? Yeah. 8.3. I read this as 8.55. Notice that it's dividing 0.5. This is, by the way, times 10 to the minus fifth meters per second squared. It's dividing that by 10, right? So each little interval is 0.05 seconds. Is that right? Yeah, that's right. Okay. Or 2 squares is a tenth, right? Okay, so I thought this was 8.55. I thought this guy was 8.8, right? And this one was 9.05. By the way, there's a much easier way to do this, but I'm just showing you what I did, right? And then I said that this middle point here was about 9.3. Why did I do that? That doesn't seem right. Oh, yeah. Right? And then basically what you're doing is you're approximating the area of this by finding the area of these rectangles, right? You can imagine this, right? We're saying that the area under this graph is the area under these rectangles, right? This area here and this area. And of course, what's interesting about this is the numerical method. So I'm a computer programmer, so of course I approach it the way a computer programmer would, right? Is that we average it and then just multiply by the width, right? So what I did was I said that it's 8.3 plus 8.55 plus 8.8 plus 9.05 plus, oops, no, I can only do those three, right? So these three are all 1 times 10 to the 7th seconds wide, right? That's a lot of time, 10 million seconds. Okay, so this one is this, right? So the first 4, and then I multiplied that by, ignore that, I multiplied that by 1 times 10 to the 7th seconds, right? And that would be the area under this. Oh, and these, by the way, have to be, each of them be times 10 to the minus 5th, right? Times 10 to the minus 5th, because that's this axis here, right? 10 to the minus 5th times 10 to the minus 5th. Or you can just pull out a 10 to the minus 5th out here. Or ultimately, I guess you could just multiply by 100, right? 10 to the minus 5th times 10 to the 7th is 10 to the 2, right? Okay, so now I've found this area here. I've found this guy. I found this guy, right? Now I have to find this area there, and that's going to be, what, 9.3 times 10 to the minus 5th. And then this is, what, 0.8 million. So 0.8 times 10 to the 7th seconds, right? And I get a delta V. And my delta V ends up being between 4,200 and 4,300, okay? 4,200 and 4,300, okay? And that's the delta V, right? And so the final velocity is going to be the initial velocity plus the delta V, right? So the initial velocity is 1,200. Right, your delta V that you get doing this, you need to do it yourself. You can do it. Okay, that delta V is somewhere between 4,000 and 5,000 meters per second. You're going to add that on, right? So that's your answer. The answer from this. Okay, and you will get, oh, whoops, that's down here. Okay, put that stuff down here, right? So it's V is going to be the initial velocity plus delta V, right? And the delta V is what you're going to find from that. The initial velocity is your 1200. There you go. And the final answer, by the way, is somewhere between 5,000 and 6,000 meters per second. Okay? Happy hunting.